All right, let's just jump straight into this explainer, because we're going to absolutely shatter a fundamental assumption you probably have about the physical world. We all naturally tend to think of mass as this absolute, unchangeable property of an object, right? A bowling ball is heavy, a feather is light. End of story. But as we zoom down into the microscopic realm of solid-state physics, that everyday intuition completely falls apart.
So I want you to imagine a scenario where mass isn't just this fixed constant of nature, but rather an illusion dictated entirely by its environment. What if an object's mass could actually change just by, dropping it into a crystal lattice? Well, today we are zeroing in on exactly that. It's a concept called effective mass. Basically, it's this crucial mathematical parameter that characterizes exactly how charge carriers, like electrons and holes, respond to external forces when they're trapped inside the incredibly complex environment of a crystal lattice.
Okay, so by formal definition, effective mass, which physicists usually denote as m star, is the mass a particle seems to have when it's responding to forces. Think of a free electron like a guy sprinting down an empty hallway. He can move totally freely with his normal resting mass. But put that same electron inside a crystal lattice, and it's like that same guy trying to sprint through a heavily crowded, bustling room. The effective mass represents how heavy and sluggish he actually feels based on all those electrical interactions with that specific crowd of atoms. Now, here's the absolute best part about this. We don't actually need to solve all the terrifying quantum math to understand how it works. We just need to look at the shape of these energy momentum curves. In the quantum world, the shape of these bands tells us pretty much everything about how a particle is going to behave. Now, physicists will gladly tell you that effective mass is mathematically tied to the inverse of the second derivative of the dispersion curve. Try saying that 3 times fast. But in plain English, it just means curvature literally equals mass. And you can see how this plays out perfectly right here. If you've got a wide, really shallow energy curve, that means you've got a high effective mass. You're stuck with a heavy, sluggish electron that has practically zero mobility. But a tight, sharp curve, that gives you a ridiculously low effective mass, creating this lightweight, lightning-fast electron with high mobility. It's just such an elegant mathematical trick, and it perfectly predicts how these particles will accelerate the second you apply an electric field. But wait, it gets weirder. Let's really push into the quantum weirdness here, because the rules get so strange. Consider this. What happens if you push a particle forward, but it literally accelerates backward? Sounds totally impossible, right? But when that dispersion curve we just looked at bends downwards, which it does at the top of a valence band in a semiconductor, the curvature becomes negative. And that gives us something truly absurd: negative effective mass. Seriously, an electron with negative mass responding to a positive force will actually accelerate in the exact opposite direction. So to keep from completely losing their minds over negatively charged particles that inexplicably accelerate backwards, physicists came up with a really elegant workaround. They invented holes. Now, as the quote points out, these are technically complex many-particle excitations, but effectively, a hole is just the absence of an electron in a valence band. By just flipping the math around, these holes magically become quasi-particles with a positive charge and a positive effective mass. It is fascinating to realize that without the crystal lattice itself, these holes literally cannot exist. All right, so how does all this theoretical math actually play out in the real world? Well, we can see it clearly by comparing the actual effective masses of a few different semiconductor materials. Notice how the effective mass is stated as a fraction of the true resting mass of an electron. In silicon, an electron has an effective mass of 0.98, so almost its normal weight. But in gallium arsenide, it drops to a tiny 0.067. The specific crystal environment completely redefines the physical inertia of the particle. But you really have to look at that 0.04 figure for germanium's hole mass. I mean, 0.04, because these holes are just astonishingly light. They respond almost instantly to rapidly changing forces like high-frequency alternating electrical fields. And this extreme lightness is exactly why germanium, a material that everyone thought was practically extinct after its glory days in the early transistor era, is experiencing this massive modern revival for high-frequency electronics. It simply outpaces the competition when pure speed is all that matters. Okay, let's take this a step further, because the story definitely doesn't end with just one static number. As you start pumping more energy or heat or charge carriers into a system, you are forcing those electrons into higher energy states. And when that happens, that perfect, simple, parabolic shape we rely on at the bottom of the energy band, it starts to warp. It flattens out and becomes decidedly non-parabolic.
And that flattening means the illusion is actively changing. In heavily doped materials, where the bands get totally packed with excess carriers, we observe crazy phenomena like the Bernstein-Moss shift. Because the band structure is non-parabolic at these higher energies, accessing those states further from the band edge actually causes the effective mass to get heavier. The electrons literally become more sluggish the more you crowd that energy band. You can actually see the real-world fallout from this in photovoltaic materials, like MAPI, which is a hugely important material for solar cells. Look at how steeply the mobility plunges at high electron concentrations. The effective mass actually doubles compared to its baseline. And since mobility is inversely proportional to effective mass, the electron mobility just completely falls off a cliff. If you are engineering a high-efficiency solar cell, ignoring this actively changing mass is going to entirely ruin your device model.
So all this brings up a pretty obvious, though kind of mind-bending question. How do scientists actually measure an invisible, constantly changing mass? Since effective mass obviously isn't a physical object we can just pluck out and place on a traditional scale, you might be wondering how physicists confidently assign such incredibly precise numbers to these quantum phenomena.
While the secret is in watching how these particles move, scientists use this absolutely brilliant technique called cyclotron resonance. First, they apply a massive DC magnetic field to force the electrons into circular orbits. Then, they apply an AC electric field perfectly perpendicular to it. When the frequency of the AC field exactly matches the electron's orbit, it resonates and absorbs energy. By measuring that resonance, they calculate the mass. But here's the catch. It requires extremely pure samples and unbelievably low temperatures just to allow the electrons to complete their orbits without crashing into impurities and scattering. And you know what? The data from these crazy, painstaking experiments reveals yet another twist. In materials like germanium, those resonance peaks shift wildly depending on the angle. This proves that in some materials, the effective mass is actually anisotropic. That means the mass literally changes depending on which direction the magnetic field is pointing inside the crystal. An electron can feel feather-light when pushed in one direction and completely heavy when pushed in another. The internal geometry of the crystal literally dictates the laws of physics inside it.
So wrap your head around this. Why does any of this matter outside of a high-tech physics lab? Well, the main takeaway here is that our entire modern digital landscape relies completely on manipulating this mathematical illusion. From the processor speed in that smartphone you're holding right now to the efficiency of the solar panels up on your roof, it all hinges entirely on the effective mass of these charge carriers. It is the ultimate invisible variable that engineers tweak to make modern technology possible.
It really makes you look at the fundamental building blocks of our universe a little differently, doesn't it? I mean, if the mass of an electron, literally one of the most basic and fundamental particles we know of, is just a total illusion created by its environment, what other constants of physical reality are just a trick of light? It's definitely a profound thought to carry with you. Keep questioning the physical world around you. And hey, thank you so much for joining me for this explainer.